Hi, everyone. So this is the lecture video for Chapter 7. Our topics are going to be on solutions and precipitation reactions. Let's go to the slides for Chapter 7 for this part. So before we can get into precipitation reactions, we need to know what a solution is first. And to know that, we got to look at what water looks like in 3 dimensions. And you guys have drawn water before as a Lewis structure, and you know that it's going to have 2 lone pairs and 2 bonds for the central atom, which makes water bent. Okay? And because water is bent, it is its electron density is more spread towards the oxygen than it is the hydrogen, due to oxygen having a higher electronegativity. You guys may have remembered that word, right? Is that when oxygen is, when you have a higher electronegativity atom, it draws more electron density towards itself. And so it's going to be partially negative at the oxygen and partially positive at the hydrogen, right? Making water very polar. Okay, so review that as well, right? So water being very polar makes it be able to dissolve a lot of compounds. So water is basically known as your universal solvent due to it having this delta plus at the hydrogen and delta minus at the oxygen. Okay. So now when water sees, say, sodium chloride, let me go to the board here real quick. So if water sees sodium chloride, which is Na plus and Cl minus, the oxygen part of water is going to be attracted to the sodium plus, right? But the hydrogen end of water is going to be attracted to Cl minus. And other water molecules will do the same thing. So what happens is water splits up sodium chloride, and so it dissolves it. Sodium chloride is no longer a solid in the crystal lattice once it's dropped in water, because water comes in between the ions and splits them apart. And that's why we see like sodium chloride disappearing. Of course, it hasn't disappeared. It's just that it is another a state of matter called aqueous, right? So it's completely dissolved now due to the water coming in between the ions and splitting it up so that it's no longer a crystal lattice. Right? All right, so back to the slides here. Let's learn some terms. So when something dissolves in another, we call that a solution. A solution is a homogeneous mixture of 2 or more things. So that salt in water example, like salt water, is a solution. Salt is called the solute, while the water is called a solvent. Okay, so the solute is anything that is in the minor component, and the solvent is in the major component. So since salt is present in less amount, we call that the solute, and water is present in a greater amount, we call that the solvent. Okay. And the whole thing, we call this an aqueous solution because your solvent is water. Okay. So whenever your solvent is water, it's called aqueous solution, or AQ for short. Okay, so we look at this picture here. We see that we have a homogeneous mixture of salt water. It's 2 components, right? The salt being the sodium chloride. And remember I mentioned that the water is going to come in between the sodium plus and the Cl minus and split them apart. And so the crystal lattice is no longer there. And so that's what we mean when we say, a salt dissolves in water. It looks like it's disappeared, but all that's happened is it's changed phase from solid state to aqueous state, right? Now, it's homogeneous mixture, meaning all parts are going to taste equally salty. So here is an example of just, sodium chloride, like your table salt solution. You can make solutions with anything, right? It could be different salts like calcium carbonate or potassium hydroxide. or lithium chloride, right? You could have solutions of those. That just means that all we're doing is we're changing out the solute. Okay. Okay, so here's that picture that that I was explaining, picture representation of what I was explaining about salt dissolving in water. So salt, table salt, right, is in a crystal lattice that is repeating 3D array of sodium plus and Cl minus stacked upon each other. When it's dropped into water, because water is so abundant, is in abundance, it comes in between the sodium plus and the Cl minus, and it starts to pull away the ions so that you don't see the crystal lattice anymore. You just see, well, it looks like pure water, right? But you see it like that because your sodium plus and Cl minus are no longer in a crystal lattice, right? They are now surrounded by water, and that's what we mean when we say dissolving, right? Another term for it is dissolution. That's the process. Dissolution is the same as the process of dissolving. So in the end, after all of the salt has dissolved, this is what it looks like on the molecular level, right? You have remember, water being polar. So the hydrogen end of water, which is partially positive, will surround the chlorides. The oxygen part of water is going to surround the sodium plus. So there's electrostatic interactions there that makes this works, right? And that's how dissolving of sodium chloride works, right? Because water is polar. Now, we don't have to have like a salt or a solid and a liquid as a solution. Anything could be a solution. There's liquid solutions. There are gas liquid solutions. There are even solid solutions. So an example of liquid solution is the stuff we love to drink, right? Like beer or wine, right? Those are mixtures of water and ethanol, right? Alcohol. Here's another example between pentane and hexane. And of course here, pentane is in the minor component. So we call pentane is the solute and hexane is the major component. So hexane is the solvent. Okay, so now we get to what we call precipitation reactions. So in a precipitation reaction, what happens is that one of the products is insoluble in water. So it's a really cool reaction where you mix two things together that are completely soluble. And then all of a sudden, a precipitate forms, like something crashes out of the solution, and you see there's clumps of solid in the solution. And we call the solid a precipitate. One example here that we can see is if you take calcium nitrate, which is aqueous, right? So it's dissolved, and another solution of sodium carbonate, aqueous, which also means it's dissolved. What happens is you form calcium carbonate, and this is gonna come out as a white precipitate. And then the byproduct, another product, is sodium nitrate, and that one's still soluble, right? So really what it's gonna look like is two completely soluble solution, and all of a sudden a solid comes out, right? It's kind of cool. Okay, so let's stop here for now with the slides. I'm going to show you guys how to figure out whether salts are soluble or not with the solubility table. So let's go to Canvas. So under week 5 module, you guys are going to find under chapter 7 slides, a PowerPoint document called Solubility Rules. Okay? You're going to want to download that. Okay, make sure you click on that and open it. Okay, so how to read this table, you're going to see that there are 2 sections and then also 2 columns, okay? So the first section is ionic compounds that are generally soluble in water. Okay, and it tells you what those are. So remember ionic compounds between metal and non-metal, right? So these metals, lithium, sodium, and potassium, okay, these ones are generally soluble. That's how you read it, right? Including ammonium, okay? But then you also have to read the column as well. There's an exception column. For these groups, right, these top two rows, you don't have any exception. So everything that contains lithium, sodium, potassium, ammonium, nitrate, and acetate ions, they're all soluble in water, okay? And then you have this third row, chloride, bromide, and iodide are generally soluble in water, but if they are paired with these metals here, silver, mercury, and lead, then they're insoluble. Right, so that's how you read it, okay? And then you got the bottom section here. Ions that are generally insoluble would be hydroxides, sulfides, carbonates, and phosphates, but you have this list of exceptions as well, okay? So before we can really write these precipitation reactions, you guys need to learn how to write the states of matter, okay? And what it means to be soluble and insoluble. So if you are soluble, then remember the state is aqueous, right? So you write AQ next to the compound. If you have a precipitate, which is insoluble, which means that ionic compound is now back as the crystal lattice, which is the solid state, okay? So if you deem that a compound is insoluble, then you're going to write S next to it, okay? So it's as simple as that, all right? I'm going to throw some examples on the board, and we're going to use this chart to determine whether it is soluble or insoluble, and then we're going to write AQ for soluble and S for insoluble. Okay, so we got these compounds here. The first one is mercury nitrate, mercury 2 nitrate. Okay, so we go back and look here. Nitrates, it says, are generally soluble, no exceptions. So I'm going to put AQ next to mercury nitrate. Okay. All right, next is barium carbonate. Barium carbonate, okay. Oh, carbonate is in the insoluble section. And I just want to check the exceptions to see if barium is on there. Barium is not on there. So barium carbonate is a solid. All right, next one is K3PO4, potassium phosphate. All right, potassium phosphate. So phosphate, okay, we can see that phosphate is generally insoluble, but the exception does have potassium in it, right? And then here it also says all potassium, right? In this section, potassium soluble. So, okay, it's soluble. So we're gonna put aqueous. Okay. PbCl2, let's check that one. Lead 2 chloride. Chlorides is in this section here. It's generally soluble. However, let's look at the exception. When it's paired with silver, mercury, or lead. Oh, okay. So when it's paired with lead, it's gonna be insoluble. And so therefore we put solid. Okay. Next up, we got cadmium 2 hydroxide. So cadmium hydroxide. Hydroxides are generally insoluble. And then we're gonna look here for the exception. Cadmium's not there. So cadmium hydroxide is a solid. Okay. Yep. So that's how you do it. That's how you figure out whether ionic compounds are soluble or not in water. Okay, so now let's continue with going back to our slides. All right, so back to that reaction. Let's look at that reaction again, the precipitation reaction between calcium nitrate and sodium carbonate to form the precipitate calcium carbonate and sodium nitrate, okay? So you see what happens here is that, well, let me write it on the board. Easier to explain. All right. So do you guys see what happened in this reaction? Is that the calcium was first paired with a nitrate, right? Remember that this is an ionic compound. So you have a metal here that is 2+ charge, right? Because calcium's in group 2A. And then remember your nitrate is negatively charged. That's your polyatomic. It's negative. And so that's why you need 2 of those. Okay, so that's your ionic compound, right? We can do the same thing to sodium carbonate. Recognize that this is also an ionic compound because that's a metal and it's plus charge. Sodium is in group 1A. Carbonate is in group is a polyatomic and it has a 2- charge. And so that's why you need 2 sodiums, right? Na2 to balance out that 2- charge. Okay. So now in forming the products, we can break this down to see how did this happen. Well, the calcium was paired with the nitrate to begin with, but in the product, the calcium's paired with carbonate. And then the sodium at the beginning was paired with carbonate, but now it's paired with nitrate. So what did they do? They swap partners. Okay. And this reaction, there's a name for it. It's called a double displacement. So basically it's a couple, right, that swap the partners. Okay, so that's how you can think of it, right? It's just like, square dancing where you do-si-do your partner. You got 2 couples and then they swap partners in the dance, okay? Except they swap in a very specific way because calcium cannot go with sodium because it's both positively charged and same charges repel, right? So they don't want to go with each other. The plus has to go with the minus so that it's really easy to figure out what the products are going to be. You just take the metal and swap it with the other non-metal, okay? And so there are no other combinations. You guys agree, right? And so that's what a double displacement is this swapping of partner. And this is how you can generally think of it for double displacement. You have A, B, okay, let's say nitrate's B, calcium's A, plus C, D. Let's C is sodium and D is carbonate. What's going to happen is A is going to go with D and B is going to go with C. So AD plus CB. Why CB? Because you always write the cation first. Okay, so this is what we call a double displacement reaction. Okay. And so precipitation reactions are a subset of double displacement reactions. In the next chapter, chapter 8, you guys will learn that acid-base reactions are also double displacement reactions. And this is how it will always work, right? Because you always have a plus here and a minus, some plus, some minus, and this plus has to go with that minus. Okay. And so that's why the calcium went with the carbonate. And why is it just CaCO3? Well, because Ca is 2+, CO3 is 2-, so you just put 1 and 1 together, right? You guys did this in chapter 6, right? When we put together ionic compounds to make them neutral, right? So it will only be CaCO3. And then what's the other product? CB. CB. So C is sodium, which is positively charged. B is nitrate, which is negatively charged. So you put 1 and 1 together there too. So you just have NaNO3, right? And then after that, you balance the equation, put a 2 coefficient in front of NaNO3, and you got your equation. Okay. Okay. Let's see. Should we do another example? Let's do zinc nitrate and sodium phosphate. Okay, and so let's practice predicting the products here. All right, let's identify. Our A is zinc, okay, and that's a cation. So what I would do is just figure out what charge that is already. Remember, zinc is one of your fixed charge ion. That is always 2 plus. So you should know that already, right? You should have memorized that. You can also look at your periodic table to see that zinc is in group 2b. So therefore it's 2 plus, right? So looking at the group number can help you with the charge there, right? Now nitrate, you also should know now, you should know your polyatomics. It's negatively charged. And you have the polyatomic list as well, right? You can always look that up. Negative, so that's why you have 2 nitrates, okay? Let's go here. We have sodium phosphate. Na is in group 1a, so it's positively charged. And phosphate is 3 minus as your polyatomic. Okay. Do that first and then predict your products, because now you know that zinc has to go with the phosphate. Okay, so the zinc has to go with the phosphate. Well, zinc is 2 plus, but phosphate's 3 minus. So how many do you have to put together to get a neutral ionic compound? Zn3 PO4 2. Okay, right? Because 2 plus times 3 is 6 plus. 3 minus times 2 is 6 minus. 6 plus and 6 minus makes it a neutral, right? And then you go to your solubility chart and look up the state for that. Zinc phosphate. Okay, we have phosphate. Phosphate is down here. Oh, and it's generally insoluble. And zinc is not on the exception list. So this is a solid. Okay, we have a precipitation reaction, right? Because this was aqueous and it turned solid. Plus, Na is going to go with nitrate. So Na is plus, nitrate is minus. So they just go 1 and 1. Na3, right? So just 1 and 1 here. Now we look up state of matter for that. Nitrate is here, generally insoluble, no exceptions. So it's going to be aqueous. All right, so now we balance the equation, right? Predict the product first, then you balance the equation. Look at all of these. You can see that it's just this one, right? It's this one's the most complex, right? Obviously. So we're going to count 3 zincs on the right side. I need to put a 3 in front of here to balance the zinc. Then I count 2 phosphates, right? 2 phosphates on the right side. Oh, there's 1 phosphate there, so I need to put a 2. And then I got 6 sodiums here. 2 times 3 is 6. So I need to put a 6 here. And then I have 6 nitrates, right? 6 nitrates, and that balances out 6 nitrates here, right? 2 nitrates here times 3 is 6 nitrates. Okay. So there we go. That's how we write precipitation reactions and predict the products for them. All right, let's go back to the slides for a second. Let me show you what it looks like in solution, what's happening. So to recall, right, we had this other precipitation reaction, calcium nitrate plus sodium carbonate goes to calcium carbonate solid plus sodium nitrate aqueous. So in solution, this is what it would look like for the solution of calcium nitrate. It's soluble, right? It's aqueous. So you have a lot of water molecules coming in between calcium 2 plus ion and the nitrate ions, right? They're just floating around and they're dissolved. Okay, and then sodium carbonate is also dissolved as well. So when you start to mix it, what you see is that the double displacement reaction starts to happen, right? So the calcium is going to come and find the carbonate, which is right here. Okay, so the calcium, these yellow 2 plus here, balls, are going to be attracted to the 2 minus carbonate, right? So when they get attracted to each other, boom, since they're insoluble, they're just going to crash out of solution, right? So as soon as these solutions are mixed, these 2 ions come find each other. The sodium and the nitrate, they're also attracted to each other, but sodium nitrate is soluble. So they're just still swimming around, okay? The only ones that collide and come out of solution and is no longer dissolved would be calcium carbonate. And that's why we observe a precipitate in the flask, right? And you will see this in one of your labs in Top Hat too. Very cool demo. So make sure you watch that. It'll help you understand it better as well, right? These slides only can do so much. Okay, so now we come to, well, let's do a couple more examples before we start writing like complete ionic and net ionic reactions. So in the homework and exams and things like that, you may have a prompt that is like, predict whether a precipitation reaction occurs when each following pairs are mixed. Something like that, right? And so let's say, A, the pairs are CaCl2 aqueous plus Na3PO4 aqueous. Okay, so first thing you got to do is just to predict the products, right? Remember, it's going to be do your partner, swap the partners, right? Notice calcium is the metal. So cation, anion, right? And it's this cation that's going to go with this anion, right? Then figure out the charge, right? In fact, put the charges on top right now. So first thing as you do, so that you don't forget the charges, and it's much easier to see how they're going to come together. Okay, so in calcium chloride, you know that calcium is in group 2A. You have your periodic table, right? So it's going to be 2 plus. Chloride is in group 7A, so it's going to be negative. And that makes sense why there's a 2 there, because a 2 plus needs to balance out with a 2 negative, right? You go to sodium phosphate, you see that sodium is in group 1A, so it has a positive charge. Phosphate is your polyatomic, is 3 minus, right? So that's also why you needed 3 sodiums here to balance out the 3 minus. Okay, so now we do the swap, right? Remember, AB plus CD goes to AD. So your calcium's got to go with your phosphate, but your calcium's 2 plus and your phosphate's 3 minus. So how many do you have to put together to make it balance? Ca3 equal PO4, 2. Okay. And then you look that up on your solubility chart. You see, oh, phosphate is generally insoluble, and calcium is not part of the exception. So that's going to be a solid. And then plus, sodium's going to go with chloride. Sodium is plus, Cl's minus, so NaCl. Okay. Then you go and look at NaCl. You see, oh, chloride is always soluble. Okay, so NaCl is AQ, aqueous. Okay. After you've predicted products, you will balance the equation now. Okay. So let's see. This is the most complex. So I see 3 calciums on the right side. I need to throw a 3 in front of here. Okay. I see 2 phosphates on the right side. Only 1 phosphate here. So I'm going to put 2 there. Okay, which makes now 6 sodiums, right? So I continue. 2 times 3 is 6 sodiums. So I need to put a 6 in front of NaCl. Okay. And then 6 chlorides, which I count over here, 6 chlorides. Okay, so now everybody's balanced. Okay. All right, so by the way, we call this equation the molecular equation. Okay. What we've been writing here is the molecular equation. All right, let's go to another example. All right, let's do another one. Yep, KOH aqueous plus FeNO3 aqueous mixed together. Okay. So in the first problem, right, well, it says predict whether a precipitation will happen. We say yes here. Okay. Now this is how it goes. If both of these are aqueous, right, we had done this and this was, the products are both aqueous, then you don't have a precipitation reaction. And in fact, you just write no reaction. Like there's no reaction. Okay. So only when you have one product is a solid, then yes, it's a precipitation reaction. Okay, so same deal here, right? We're gonna put charges on top of here then first. Potassium we know from group 1A is plus. Hydroxide is your polyatomic, is negative. Which you can find on your sheet, right? For iron nitrate here, FeNO3. Remember, iron, when you look at your periodic table, it's not a fixed charge metal. So you realize, oh, I don't know the charge of iron. Iron, I have to figure it out from the polyatomic. Here, the polyatomic nitrate is negatively charged, but you got 3 of them. So that's 3 minus total. That means your iron has to be 3 plus, right? So put that on top. Okay, so now you know everybody's charges. You can put it together. So your A is going to go with D. So plus and a minus. Great, that's just 1 and 1. So KNO3 or potassium nitrate. Okay, and then your other product. Iron is going to go with hydroxide, but iron is 3 plus, hydroxide is just 1 minus. So we need 3 hydroxides to 1 iron, right? Do iron. And then hydroxides in parentheses, little 3, okay? And then now we can look it up, right? Potassium nitrate, solubility chart. Oh, nitrate, it's always soluble, no exception. So you go AQ. Then we go to iron hydroxide. Let's see. Hydroxides are generally insoluble, and iron is not part of the exception. It's a solid. So again, here you're going to say, yes. Yes, it is a precipitation reaction. Okay. And we call this, again, the molecular equation. Okay. All right. So now let's move on. I'm going to show you guys, it's called a molecular equation because all of the things, all the compounds, the way we write them are stuck together, right? They're stuck together, implying that they're in a crystal lattice, right? The way we write it, it's implying that it's in a crystal lattice, like it's, stuck to each other. However, remember that in the aqueous state, they're not stuck together. Water has come in between them, actually split them apart. They are not even touching, right? That's like when water comes in between and pulls apart 2 magnets. It's no longer in the solid state. It says aqueous, right? And so the molecular equation isn't exactly accurate, right? Or it's not as descriptive, right? It's not really true to what's happening in solution. And so that's why we start to write complete ionic equations, and then, complete ionic equations, and then we write net ionic equations. Okay, so let me show you guys how to do that. I'm going to show you with this example here that we've already done. Balance. Okay. So I'm going to call this, right, the molecular equation. Okay, and then we go to complete ionic equation, and I'll just write EQN for short. In the complete ionic equation, remember what we said? Things that are aqueous are not stuck together because water's come between them and separated the ions. Okay, So in the complete ionic equation, anywhere you see aqueous, you're going to split up all the ions. Okay. So for CaCl3, okay, if I just had CaCl3, for example, water is going to come in between and just pick all of the ions apart. So what ions do I have? I have a calcium ion of 2+, and I have 3 chloride ions. So I actually have this formulation, right? And water is just come in between and just split all that up. Whereas without water, all of these were, sorry, this is CaCl2, not 3. That makes sense, right? Because it needs to balance. So you have, right, what you have is without water, these would be attracted to each other, and they're forming a cat crystal lattice, right? But if water comes in between, then it's just going to split it all up. And so that's how you should envision it, right? As water comes in between, it splits these all up. So in a complete ionic equation, what you're doing is you're going calcium. How many calcium ions are there? Well, in one, there's 1, but I have a 3 in front here. So I have 3 of these, which means I will have 3 calcium 2+ and 6 of these, right? Because I have 3 times 2, 3 times 2. So I will have 3 Ca2+ aqueous plus 6 Cl- aqueous. Okay, that's how I'm splitting this up. And then here, how do I split this up? That's 6 sodiums. And sodium's what charge? Plus. That's a plus. Okay. And phosphate is 3-. Okay. And then I keep going, right? If I see a solid, I don't split it up because it's in a crystal lattice. So it should be written stuck together. So I leave it alone. If I don't see aqueous, I don't split it up. That's the rule for complete ionic. I see aqueous again, I split it up. So that's 6 sodium. Remember, sodium is positively charged. Plus 6 Cl- aqueous. Okay. So notice that I'm using the coefficients, and anytime I see aqueous, I'm going to split it up. But if I have a solid, I leave it as is. And so that's why it's called a complete ionic, because we're writing ions, right? What are the ions in solution? So don't make this rookie mistake, okay? I see a lot of people just write Ca and Cl. No, it's not Ca, it's Ca2+. Totally different things, okay? It's not Cl, it's Cl-. So make sure that you are writing ions. That's why it's called complete ionic equation. So make sure you have the charges in there, okay? Then the third type of equation you should know how to write, it's called a net ionic equation. And for the net ionic equation, you will knock out what are the same on both sides of the complete ionic equation. So look at the complete ionic equation. What are the things that appear on both sides exactly the same? I see a 6 sodium plus, a 6 sodium plus, I can cancel those out. It's like math, right? Cancel the same things out on both sides. And then I got 6 chloride here and 6 chloride there I can cancel out, right? Both are aqueous. And what I have left over that I did not cross out is my net ionic equation. So that'll be 3 calcium plus a phosphate goes to calcium phosphate. Solid. Okay. So you see the net ionic equation is just showcasing for you what is happening. Only the precipitation reaction is happening, right? Not all the other fluff, right? And so the things that I cross out, we actually have a specific name for these. It's called spectator ions. Okay. So here my spectator ions are my sodium plus and my Cl-. Okay, it's the ones that you cross out. Why are they called spectator ions? Because they're just watching. They're not part of the cool precipitation reaction, right? They're not a part of that reaction. They're just swimming around in water, right? And from the equation, you can see that they are spectating, as in nothing has changed for them. So for example, the chloride and the sodium on the left side were aqueous, and on the right side, they're still aqueous. That's why they're spectators, right? Whereas here, the calcium and the phosphate were aqueous, but then they turned solid. So they've changed state, right? And that's what tells you that there's a reaction going on. If you didn't change state, then there's no reaction for you, right? So the net ionic equation is the star of the show, right? That's basically your main event, and that's what you write is that precipitation reaction. Okay. All right, let's do another one. And let's do it with a prompt and everything too, so you guys can see how it is. Predict the following. Predict the products for the following precipitation reaction, and write the complete ionic and net ionic equations. Okay, so there we go. We have lead 2 acetate plus potassium iodide. Okay, remember, before you can predict, you need the charges, right? So you can look here, you realize, oh, lead, that's not one of my fixed charge ions. It's in the transition metal. So I need to look at the nonmetals, right? The anion to figure out the charge for the cation. Well, acetate is negatively charged, but I got 2 of them. So that's 2 minus, therefore my lead has to be 2 plus. Okay. Potassium iodide, oh wait, potassium is a fixed charge metal. I can figure that out because it's in the periodic table, group 1A, and that's plus. So iodide is minus, okay? And now I need to put lead and iodide together so that they're neutral. Lead is 2 plus, iodide is just minus, so I only need 2 iodides, right? And then I look at my solubility chart and I see, oh, iodide is generally soluble, except for when it's paired with lead, and it's insoluble. Okay, so I do have a precipitation reaction. I'm going to put solid there. Plus, what's the other product? Potassium's going to go with acetate, 1 and 1, right? Because potassium is 1 plus, acetate's 1 minus. So you know KC2H3O2. And then you're going to go to your solubility chart. And you're like, oh, look, acetate is generally soluble, no exceptions. So that's aqueous. All right. All right, after you predict the product, now you balance the equation, right? Put your finger on the most complex. Lead, 1, 1, acetate. I got 2 acetates, so I got to throw a 2 in front of here. And now I got 2 potassiums I need to balance, so I need to throw a 2 in front of here. And then now I have 2 iodides, though. And look on the other side, I do have 2 iodides. I'm good, right? So always start with your molecular, right? Now this is called molecular equation, right? The molecular equation is a balanced reaction after you've predicted the products, okay? Now it says, write the complete ionic and net. So I'm going to do complete ionic. Remember, in complete ionic, anytime I see aqueous, I'm going to split it up, right? So I see aqueous here. I know that PB is 2 plus, so I'm going to write PB 2 plus aqueous plus. I see 2 acetates, right? So I go C2H3O2 minus, but 2 of them, so I put a 2 in front. Aqueous, okay. Plus, that's 2 potassium iodides, right? 2 Ki, so that means 2 potassiums. Because this is aqueous, gets split up 2. And that means 2 iodides, so 2I minus. Remember to have the charge, okay? 2I minus aqueous goes to, do I split this up, guys? Not the solid, so PBI2 solid gets just written as is, right? Stuck together. And then aqueous here, I need to split this up. That's 2 potassiums, so 2K plus. Aqueous plus 2 acetates, C2H3O2 minus aqueous. Okay, that's my complete ionic. Okay. Now I get to my net ionic. I'm going to cross everything that is the same on both sides. And I see it's this, the acetate and the potassium. And then what's left is Pb2 plus aqueous plus 2I minus aqueous goes to PbI2 solid. Okay, that's my net ionic. And then as always, I'll ask you here, right? Name the spectator ions. Almost always I'm going to ask you, right? So you might as well just write it. Spectator ions are the ones you cross out, are the ones that didn't do anything, right? So K plus and C2H3O2 negative. Okay. All right, so we've done 2 problems here, and you guys can see how that works. It's a progression, right? If you start out with the correct balance molecular equation, these just go boom, boom. They just fall right into place, right? You just have to split it up. But you can imagine how catastrophic it would be if you didn't start with the right molecular equation. You'll get the rest of this wrong, okay? Or if you didn't have it balanced, you still get the rest of this wrong, okay? So that's why it's crucial that you guys really know how to, this is where it's at. This is what you're practicing a lot until you really can get that. And then these come a lot easier, okay? So, you know, on our next quiz and on the exam, you know, you're going to be doing this. And you really want to be careful that you're always having this molecular equation spot on, okay? Otherwise, you're going to miss all of this, okay? And so you're going to miss a lot of points then, you know, on the quiz or exam if you don't get this point, right? Okay, well, let's do another example, right? Practice, practice, practice. Okay, so again, first thing before you predict the products, let's get the charges up there so that you can do that part easily, right? Lithium is in group 1A, so it's plus. Carbonate is 2 minus for your polyatomic, and so that's why you need 2 lithiums, right? Go over here, barium is in group 2A, so that's 2 plus. Br is in group 7A, so that's negative, right? Easy peasy, okay? So now lithium's gonna wanna go with Br, right? So it's 1 plus and 1 minus, so it's just going to be 1 and 1. Lithium bromide. Okay. Look it up. Lithium bromide. Bromide is generally soluble, no exceptions. So aqueous. Plus, what's the other one? Barium is 2 plus, carbonate is 2 minus. So they go 1 and 1 too. Wow, easy. Just like that. Then you look up solubility chart. Carbonate is where? Down here, generally insoluble. Barium is not on the exception list, so it's insoluble. Wait, we do have a precipitation reaction. And now we want to balance it. So lithium carbonate, 2 lithiums, so I got to throw 2 in front of there. 1 carbonate, great. 1 barium, 2 bromides, 2 bromides. Wow, that was it. All I need to do was put a 2 in front of lithium bromide, and I'm good. Okay, so again, remember, this is called the molecular equation. Okay, then the next one is to write the complete ionic. Okay, remember how that works? Complete ionic, wherever you see aqueous, split it up. So I see aqueous here, that's 2 lithium plus aqueous, plus a carbonate, CO3 2 minus aqueous, plus barium, 2 plus aqueous, plus 2 Br minus aqueous goes to, this is aqueous too, so you split it up as well. 2 lithium plus aqueous plus 2 Br minus aqueous plus, this one you don't split up, right? Because it's a solid, BaCO3 solid. Okay. Then in your net ionic, you're gonna cross out 2 lithiums and what else? The 2 bromides. Okay. So what's left? CO3 2 minus aqueous plus Ba2 plus aqueous goes to BaCO3 solid. Okay. With your spectator ions in Br minus and lithium plus. Yep. Okay. Yeah. All right. One more. Let's do one more. All right. So again, before we predict the products, let's get the charges up there. Zinc is 2 plus because it's in group 2B on your periodic table, right? Nitrate, NO3 is minus. That's why you need 2 of these, balance out the zinc. And sodium phosphate, sodium is in group 1A, so it's plus. You look at phosphate, it's just 3 minus, right? And so that's why you need 3 sodiums in order to do that. So now you're gonna do the swappy swap. Zinc's gonna go with phosphate, but zinc is 2 plus and phosphate is 3 minus. So you're gonna need 3 zincs and 2 phosphates. ZN3PO42, right? Make sure you put the PO4 in parentheses to say I got 2 of those units. Then I look at my solubility chart. Phosphate is in the not soluble, and zinc is not one of the exception. So it's insoluble solid. Okay. Plus, what's the other one? Sodium is plus, and it's going to go with nitrate, which is minus. So that's just 1 and 1. NaNO3. And then I go to my solubility chart. Oh, nitrate is soluble, no exception. So aqueous. Okay. Next step, balance it, right? Most complex is that. So 3 zincs. Let's throw a 3 in front of here. 2 phosphates. Oh, I see 1 phosphate on the left side, so I got to put a 2. That makes it 6 sodium, so I got to go over here and put 6. But then that's 6 nitrate, and I count. Oh, that's 2 nitrate times 3, 6 nitrate. So now I'm balanced. Yeah. Remember what this one is called? The molecular equation. Okay. Then I go in with my complete ionic. Same thing every time, as you guys can see, right? I see aqueous, I'm gonna split it up. That's 3 zinc 2 plus aqueous plus 6 NO3 minus. Why 6? You got 2 here already, right? 2, but then you multiply by 3. Okay. Plus 6 sodiums, right? 2 times 3. 6 sodium plus 2 times 1 here, so 2 phosphate, 2 PO4, 3 minus aqueous goes to. We don't split that up, so zinc, ZN3PO4, 2 solid, plus, here you do split up, so 6 Na plus aqueous, plus 6 NO3 minus aqueous. Okay. Net ionic. Okay, let's see what we can cancel out. Same on both sides, guys. You see it? 6 sodiums and 6 nitrates. So we have 3 CN2 plus aqueous plus 2 PO4 3 minus aqueous goes to ZN3 PO4 2 solid. Okay. Spectator ions. Na plus and NO3 minus. Okay. All right, guys. Go knock them out and practice. That's the only way you're gonna get this, right? It may seem very complicated. It's not. It's the same thing every time. And if you know your polyatomics, and you should, and plus you have the sheet, right? Get it out and just knock some of these out. And I'll see you guys next time.